Hello, Audrey.
Hi.
All right, that's the star of the video is already passed. So this video is going to be about water potential. Oh goodness. So we're going to review in this video some of the basics, and then the next video is going to be a little bit more advanced in the stuff that we'll also do in class. We looked at 3 different types of solutions, and we experimented with them: hypertonic, isotonic, and hypotonic solutions. And in those names, we're talking about the solute that is dissolved in the solution being hyper or iso or hypo with respect to the cell in question that is in the solution. And I had told you we had a couple ways to remember these. So over here we've got our little hyper skinny guy. He's skinny because he's very, very hyper, moving around all the time. And over here we've got our hypo hippo. And those relate to what happens to these cells when they are in the various solutions. So let's start off with our isotonic cell here. It's isotonic because it has the same concentration of solute on the inside and outside of the cell. So this entire time that it's in this solution, it's going to have water movement out and into the cell. And what's it going to move across? Well, it's going to move across the cell membrane. This is a square cell. I drew it that way because it's representing a plant cell, because we use potatoes for it. But the cell membrane is really the limiting factor in where the water is going to go. The cell membrane is permeable to water. It is not permeable to large molecules or strongly charged molecules unless there is a, I need my pen, unless there is a protein in the cell membrane that allows for those molecules to pass through. And those can pass through passively sometimes if there's a protein involving a particular type of molecule that will allow it to move down its concentration gradient from high concentration to low concentration, like over here. Or sometimes they're active transport proteins where they will actually transport some of those particles uphill from low concentration up to high. And those ones are active because they require energy input. But today this is all about water movement within these cells, and want to refer to these guys particularly. So these particles are representing either large molecules like sucrose or glucose, something like that, or they could be small charged molecules that are strongly charged, such as like sodium and chlorine ions like salt. And even if they're really tiny, they've got a ring of water molecules around them. It's called a hydration shell because of the polar nature of water. Those little guys aren't able to pass through the cell membrane because of that hydration shell of water that is going to hang around them. All right, so isotonic solution. Nothing exciting happening. We've got water moving out, water moving in, and it's happening at about even rate, so there is no net movement. Ooh, that's sloppy. All right, no net movement of water within our isotonic system. In the hypertonic solution, we saw this happen, so that was really exciting. Again, these particles can't cross the cell membrane. It's not permeable to them. Semi-permeable membrane. It is permeable to water. The cell membrane has some proteins within it that are called aquaporins, which are specifically for letting water through. And the cell membrane itself can occasionally let some water molecules pass through. By occasionally, we're talking about lots and lots per second, because cell membranes are large with respect to the billions of little water molecules around them. So in this example, the hypertonic solution, water is going to have a net movement out. There is going to be some water moving in and some water moving out, but we're going to have a net movement of water out of the cell. And eventually, later, the cell membrane is going to have pulled away from the cell wall. Eventually, it will reach equilibrium because the concentration on the inside of the cell is equal to the concentration on the outside of the cell. And that's where we had like the flaccid or limp carrots and potatoes. We couldn't crack them anymore. This happens to your your vegetables if they sit in the refrigerator too long, or your flowers if you don't put them in water after your boyfriend gives them to you. So eventually they lose their water and they become limp because there's no pressure to hold this cell wall in place, and the cell wall is not super strong without the water holding it in place. With our hypotonic solution, we had the water moving the other way. So we had a net movement inside the cell. That makes sense here. We use distilled water. So even though I've got like a couple little specks on the outside, ours had pretty much nothing on the outside. And so we're left with, in a hypotonic solution, a cell that looks like a hippo in the end. It swells up. So we had something like this. It looks kind of like a potato, funny enough. And it was turgid, or it had lots of what's called turgor pressure within it, because there was a lot of stretching of the cell up against the cell wall. But I do want to ask an interesting question here, and nobody brought this up in class. We would have expected that this still doesn't look like it's in equilibrium. I hope you don't think it looks like it's in equilibrium just from the picture there. So you might have expected that we would come back and we'd find a bunch of mushed up potato that had exploded out because the distilled water would tend to keep going on in more and more and more. And there's a reason that this did not happen with the potato, and it has to do with the fact that we used a potato cell for it and not, like an animal cell. So what do animal cells not have that plant cells have? Well, we got a few examples, but there's one critical thing, and it relates to this. So I got a little simulation for you. We're going to start off with an animal cell placed in distilled water. That little guy there is a red blood cell. So, oh, goodness, that wasn't very exciting. Replay. Refresh. Oh, this video is gone bad. Let's see if I can go back to this. Hold on. I swear it worked really well the first time. Let's try it again. Okay. Water's moving into the cell. The red blood cell expanding more and more and more, getting more and more like a hippo. But eventually, that cell membrane can't hold everything forever. You keep putting air into a balloon, and it will burst. That was much more exciting. All right. But we did this with potato cells and carrots, and there's a reason that they didn't explode like the red blood cell. Water goes in. Cell starts to swell. Our hippo is happening there. And what happens on this one that didn't happen on the other one is that the cell wall starts to exert pressure. So we've got a limitation to how far this cell can expand. And at this point, we've got a net force of 0 because there's obviously water trying to get in from the outside. But there is actually a force being exerted against it. So we're going to learn about water potential, and water potential is going to reduce all of these things down just to forces, and we're actually going to treat them like atmospheric pressure forces. So there's pressure pushing the water in, and there's pressure keeping that water out, and this cell is at equilibrium. It might still look like this guy and have a whole bunch of solute still on the inside of it, but it's at equilibrium because there is a cell wall preventing it from exploding. And that is where we're going to head with the more advanced topic for the next video of water potential.